This lecture is going to be on seismic waves. We're going to be looking at earthquakes and detailed features of them. We're simply going to be saying that plates or rock moves, and then waves are created. To start off with some terminology, let's make sure we identify what the focus of an earthquake is and the epicenter of the earthquake. And notice this cross-section is what I'm going to be referencing. Earthquakes result when rocks move, releasing tremendous amounts of stored energy all at once. Waves move outward in all directions from the focus. So these are wave fronts that are moving out from this location. And the focus is the precise location in which the earthquake occurred. Faults, you can see this line here, or a plane here. These are planes of crustal rock that move, generating the earthquake. So this plate on the left side, or this rock itself, might be moving, say, up in the picture, and this rock here would be moving relative to it would appear to be moving down. But what we have here is we have a tremendous amount of energy that is built up here. In the instant in which this area, or this would be the focus, so this is the point in which the rock moves, all of that energy that was stored is released at once. So a little bit more on the focus and epicenter. The point in which a seismic wave originates due to rock moving is the earthquake focus, or foci plural. Earthquake foci can be found at different depths below the Earth's surface at 3 different levels. We can look at shallow earthquakes, 10 to 70 kilometers, intermediate 70 to 300 kilometers, and deep from 300 and above kilometers. Shallow earthquakes are generally the most destructive. In terms of shallow, intermediate, and deep, they are related to the type of boundary in which the earthquake is observed. So if you think of a deep earthquake, I would say it's probably in your best interest to think, well, if it's a deep earthquake, we're looking at something that is subducting. It is a slab of oceanic crust. Sometimes even intermediate are associated, but you would find shallow, anytime you have that just rock move, all of that energy is released at once. The epicenter of an earthquake is the point above the Earth's surface that is located directly above the focus. In other words, it's on the surface, it's directly above the focus of the earthquake itself. So the instant in which an earthquake occurs, you've got all kinds of different waves that are sent out. So we're going to study these. We need to make sure we pay attention to what is happening with the primary wave, the secondary wave, and my 2 surface waves, Love wave and Rayleigh waves. So different types of waves occur upon the release of the energy. You have your primary waves, they travel the fastest. You have secondary waves, they arrive second, they travel second fastest. And then you have 2 types of surface waves that really do the damage to structures and buildings and homes, Love waves and Rayleigh waves. We're first going to explore P waves. A P wave is a primary wave. P waves are what are called compressional waves, also longitudinal waves, sometimes they're called pressure waves, because the rocky material in their path moves back and forth in the same direction that the wave travels, alternately compressing and expanding the rock. So let's imagine we have a slinky. If I push and pull the slinky, the coils are going to compress together and spread out in different regions, and that wave is going to travel from left to right. So if I'm a coil, if I'm a coil and this wave is traveling through me, I'm going to move away, back, but I'm going to end back, and my final location is going to be equilibrium, right back where I started. That the wave is simply energy just traveling through this medium. So this is an area where it's spread out, this is an area where it's compressed. And we call these compression regions, we call these expansion regions. Technically, these are referred to as rarefactions. But in this case, we're looking at compressions and expansions, and we can see that with the coils. P waves are the fastest seismic waves. They travel in strong rock or dense rock at about 6 to 8 kilometers per second. That's about 3 to 5 miles per second. So these are moving very, very quickly. So what are S waves? Well, S waves are secondary waves. They're shear waves. They have this twisting element to them. Rather than compress the rock themselves, they travel through. S waves travel at about 3.5 kilometers per second, about 2.2 miles per second. S waves cause rocky material to move either side to side or up and down, perpendicular to the direction the waves are traveling. So let's look at this rope for a second. Let's say I move my hand this way and this way. It's going to send what we could call a pulse. If I'm the rope here, I'm going to actually move side to side before I go back to my original location. So notice this rope here would have gone this way, and then this way, and then back to its original location as the wave travels left to right. So if I'm the rope, I'm moving perpendicular to the direction in which the wave is traveling. So both primary and secondary P and S waves help seismologists to locate the focus and the epicenter of an earthquake. So once again, let's look at this S wave, kind of the wave properties. If the travel is from right to left, so the wave is traveling this way, it can move either up and down, which is still perpendicular left to right, or it can move kind of this to and fro, this to and from. But either way, it's still the particle motion is perpendicular to the direction which the wave is traveling. And finally, let's look at surface waves. Earthquakes generate surface waves that travel out from the epicenter along the surface of the Earth. The two types of these surface waves are called Rayleigh waves, named after a British physicist Lord Rayleigh, and Love waves, named after a British geophysicist A.E.H. Love. Surface waves cause damage to structures as they shake the ground underneath the foundations of the buildings and other structures. So love waves, these are horizontal transverse. So as this wave is traveling left to right, if I imagine these blocks as the ground, these are going to be moving left to right as the wave is traveling to the right. Well, in this case, perpendicular to it. So it'll be, based on the picture, it's going to be kind of up left and then down right as the wave travels from left to right. So pay attention, this is perpendicular to the wave direction. Then I have Rayleigh waves, and these are rolling waves. And if you notice, the waves as it's traveling from left to right, it's this rolling action. And they're pretty interesting to see when you look at these dynamics of it, that these types of waves, your Love and Rayleigh waves, are just characteristic of really destructive waves that we find on the Earth's surface. So earthquakes generate all of these types of waves. An earthquake will generate all of these types of waves, and they will propagate over the surface of the Earth and through the body of the Earth. The waves can be distinguished by the different velocities and particle motions. Seismometers measure the particle motion produced by these waves. So remember, we can look at the different types of waves. We just studied body waves. We're going to be looking at longitudinal waves that we call P waves. We're going to look at transverse waves that we call S waves or secondary. So we have primary and secondary waves. These are body waves. These we'll look at here in just a few minutes and describe how they travel through the Earth. And remember, P waves travel at about 3 to 5 miles per second, whereas S waves, secondary waves, travel at about 2.2 miles per second, or 3 to 4 kilometers per second. And surface waves travel just slightly faster than Rayleigh waves. So we kind of have this sequence. We have primary waves, we have secondary waves, we have Love waves, and then Rayleigh waves. Rayleigh waves are described as 90% of the S wave speed. But this is the sequence in which the waves occur or arrive at a seismic recording station. So let's explore the particle motion in the wave direction one more time. So in this case here, as a P wave passes, the ground is vibrated in the direction that the wave is propagating. So in other words, if it's moving from left to right, if I am the ground, if I am rock in the ground, I'm going to move left to right as the wave travels through me. So that's simply considered parallel or in the same direction as the wave direction. And here, as a transverse wave passes through, the ground actually moves perpendicular to the direction that the wave is propagating. S waves are transverse waves. So if this is traveling from left to right, direction of wave propagation, you would find that if I'm a particle of the ground, I would be moving perpendicular to it. I would be moving up and down based on this picture. So longitudinal waves, the wave propagation is in the same direction of particle motion. In a transverse wave propagation or direction it's traveling is perpendicular to the particle motion. So P and S waves are very significant. These are called body waves. They travel through the Earth. And we're going to look at that right here. You'll see that these body waves, P and S waves, they travel through the Earth, and you're going to find that these are what are going to tell us what is happening within the Earth. It's very important we understand how to interpret these. Primary waves travel through all types of media. They can travel through solids, liquids, and gases, and that's relevant because remember, the liquid outer core is a very specific, let's just say a phase change, but primary waves can travel through them. Secondary waves, or transverse waves, they cannot travel through liquids, and this is very significant. So they only reflect back at the mantle core boundary. Remember, the mantle core, we're going to see this coloration here. We see some of these waves reflect back. Well, both primary and secondary waves reflect back, but secondary waves are unable to travel into the liquid or the fluid outer core. Primary waves can travel through it. And when we look at what's happening with the primary wave, we can actually see that it's bending or refracting as it's traveling through the different media. We're going to explore that a little bit further. The picture to the right shows P waves that reach a boundary, such as the mantle outer core boundary. Both reflect and refract into the liquid. When I say both, technically I'm talking about P waves both reflect and refract, not both types of waves. So just to clarify that. Whereas S waves only reflect at this mantle core boundary. Both of the colors are indicated in the picture. So notice the P wave is dark blue. So the P wave is out ahead of the S wave. Remember, it travels at a greater velocity. So I see this dark blue reflecting back. I don't know if you can see it right here, trying to hover over it. And the well, let's say this color blue, the lighter blue, here, these do not infiltrate or penetrate into the liquid outer core. Remember, secondary waves, transverse waves, are unable, they cannot travel through liquids, so they simply reflect back. So hopefully there's an overview, and that helps you make sense of different types of waves.